So hello, my name is John Crepezzi. I'm a software engineer at GitHub, and I'm actually based in Monmouth County, New Jersey. So this thing did not have to fit in an overhead compartment to get here. At GitHub, I work on things like the profile page, the contribution graph, and the timeline, and hover cards. I really like programming in Ruby. GitHub, for the most part, is written in Ruby, although we do have a bunch of Go services, and more are writing software in Go. We also have a couple Go job openings. If you're interested in working at GitHub, I would love to talk to you. Just find me outside afterward. Ruby is the language that I've been working in primarily since about 2009. And I really, really like it. In my free time, though, I really enjoy building things with my hands. So in particular, I find getting away from my desk for a little bit and focusing on something that isn't just code is a really good kind of release and gets me doing something other than just sitting in a static position. In particular, though, because I'm kind of a super nerd, I like to build things that exist at the intersection of technology and the physical world. So think like wood, metal, but then also code, because there always has to be code. A lot of times these projects aren't very useful, but they are kind of like artistic or quirky, and they're always fun. Best of all, I always end up learning something new. And when I work on projects like this, physical projects that involve code, I actually prefer to work in Go. That's why I'm here. There are a few good reasons why Go is a great choice for programming custom hardware, which I'm going to get into as part of this talk. And the hope is that maybe by the end of this presentation that some of you might be motivated to build something crazy like this yourself. So this is my daughter, Ruby. She's 7 years old. I really like her. Thank you. You know, maybe someday we'll have a kid named Go, but not yet. At Ruby School every year, there's an expert fair. An expert fair is kind of like a science fair where the kids end up making a report and a trifold board about a topic of their choice. And the parents in our town, for whatever reason, go pretty overboard with this. Last year, there were presentations that had things like live animals. And I'm not talking about just like gerbils or hamsters or something. There were like goats and cats. So needless to say, the expectations for the expert fair are pretty high. My daughter chose the Leaning Tower of Pisa as her topic because we had visited there a couple years earlier. And she asked if we could build a real leaning tower to accompany her presentation. I love projects like this that are pretty open-ended, things like build an open Leaning Tower of Pisa. And I tend to be pretty much an overachiever, so we ended up building this. This is an 8.5-foot tall Tower of Pisa. It is built of wood, but you probably noticed it doesn't lean. This is kind of like a critical flaw in our Tower of Pisa. That is, it doesn't lean until you hit this red button. And when you hit this button, the tower leans 5.5 degrees to match the lean of the real tower. So here, check it out. So this leaning tower is actually powered by Go. While it leans, it plays Tantarella, which is like a little bit of cultural misappropriation because anyway, I'm Italian, so it's allowed. And the button includes things like debouncing because kids love nothing more than finding a big red button and just hitting it over and over again. The code for this leaning tower was written in under an hour, and the best part is that my daughter, who again is 7 years old, understands the main part of the code. Okay, so let's get started. We should start by covering what type of hardware is feasible to even program with Go. When people think of custom hardware programming in 2019, they likely think of these two options, Arduino and a Raspberry Pi. They look pretty similar, but obviously these are completely different things. Other than just having a bunch of like metal and computery, complicated-looking things, there are major differences between them. So let's start with Arduino. Arduino is an Italian-made open-source microcontroller. It is built from the ground up to be programmed. Your code that runs on Arduino will actually control the hardware directly. So Arduino can technically run anything that can produce machine code that can run on the processor sitting on the Arduino. Supported by Arduino directly and kind of like the blessed languages of Arduino are C and C++. Due to size restrictions on the physical device, it's pretty infeasible to run the Go runtime on Arduino. That hasn't stopped people from trying. There have been some attempts in the past. There have been some attempts that fell apart for reasons other than technology reasons. I'm not saying that it won't happen, that we won't see Go run or produce code that runs directly on this hardware, but it's going to be a while before it happens. So whenever you hear something like that, your next obvious thought would be that there should be like a transpiler. A transpiler would be another option for programming Go that eventually lands code onto the Arduino. But if you think about the complexities with writing Go code that turns into C code, that gets compiled to machine code, that lands on Arduino, it's probably also a little bit more complex than the payoff will be. Currently, the most popular way that people are interacting with Arduino using Go is with a package like GoBot IO. GoBot IO, for those of you that don't know of it, is a great package. There's, I think, 35 different platforms that you can interact with. A lot of the stuff that I'm going to talk about today, you can actually do with GoBot IO. But GoBot IO's solution on Arduino looks like this. So there's actually a minimal program running on the Arduino, and you have to have a physical computer tethered to the Arduino, sending commands down to it on how to control the pins. This is expensive, it's pretty unsatisfying, and I think just like it's not what's in our head when we think about custom hardware. The other common option for programming hardware now is Raspberry Pi. These are made in England. Raspberry Pi, as opposed to the Arduino, is a real computer. It's got things like HDMI, Bluetooth, onboard Wi-Fi, audio out. It's not a very fast computer, but it's also not a very slow computer, and it costs $35, and it's around the same size as the Arduino. When people think of Pi, they probably think of a few standard use cases for Pi. Computer powering a display or a kiosk, some type of smart internet-enabled device like this weather station terminal. The most popular would be this RetroPie, which is a software for playing retro and console games on kind of a custom-built piece of hardware. If you're wondering why RetroPie has an E in it, I don't know. I find it really annoying too. That aside, these are all perfectly valid use cases for the Pi, but one thing that's really often overlooked is this area right here. This area is called the GPIO bus. GPIO stands for General Purpose Input-Output. And in my opinion, this is kind of like the big deal of the Pi. This is the most consequential piece of a Raspberry Pi. At its most simple, any of these GPIO pins can be set into either output or input mode. And as an output, each of these pins can only be set into two modes at its most simple. They can be set into high voltage mode or low voltage mode. As a demonstration of what that all means, we will go through the Hello World of hardware hacking, which is a blinking LED. That's like the typical first project that you would do on any platform. So when an output pin on the GPIO bus is hooked directly to an LED, just high voltage will turn the light on, and low voltage will turn the light off. So let's just walk through some code to make a light blink. First, we open up a GPIO connection, which is essentially allocating an area in memory for interacting with the GPIO pins, and we defer to close it when we're finished. Then we create a reference to a pin that is where the LED is actually hooked up to, and this pin will designate as an output pin. And then we just loop forever, toggling the state of the LED on and off. So waiting 1 second between, the LED blinks on and off. This code is pretty easy to read, but more often than not, even with simple things like this, we end up encapsulating this behavior in an interface to make it even simpler. I call it object-oriented programming. Thank you. By defining a struct to contain the behavior of this LED, we can abstract away the necessity of having to know that you have to set the pin into output mode, and we can provide nice methods for interacting with the LED. So just note here that the toggle method is directly calling pin.toggle. And I hope that that kind of helps to illustrate just how analog electrical engineering is to programming. High voltage is essentially just true. Low voltage is essentially false. And an LED is a physical device that is essentially a method that takes one input and one output, which is turning the light on or off. And that's really the mindset you have to get yourself into when working with these things. Also, one of the most beautiful things about this marriage that I'm kind of describing between physical objects and code is that when you have learned how to program a blinking LED, you have two different ways that you can go to bring the project to the next level. You can either increase your workmanship and maybe do something like build a box around it and make the sign blink, or you can increase the programming maybe by adding multiple lights or sequencing the lights or blinking out patterns. Now quickly, we'll go through the other half of GPIO, which is the inputs. In this case, you connect something like a button to the GPIO pin. You can read the current state of the button. So this is the button at a given time. You can read whether or not the button has been pressed. This particular library we're using leans on Go's closures to provide a nice way to manage the changing of the state of the button. So this edge detection allows you to specify what kind of event that you're looking for. So something like edge falling is when something that was true becomes false, and something that is edge rising is when something that is false becomes true. This edge detection, really, really important to note, doesn't exist in hardware. So there are things like interrupts to know when the state changed, but really the software at its core is working directly with the hardware, essentially polling the device to figure out when the input changed and then triggering this closure on the proper events. So now that we know how to work with inputs, the possibilities really open up. You have a device that you could program that has some inputs and some outputs. We can easily use the knowledge that we have described so far to make things like games or interactive displays or that popular traffic light deploy status indicator. OK, so time to get a little bit more complex. You're probably wondering what this is. I'm calling this a PVC Marimba. I made it specifically for the conference because I thought it would be fun to have something to show you that is bring something that looks approachable. So I built this just for here, and it's obviously built from just kind of like scrap that I had around my workshop. And it's a demonstration of what you can do, hopefully with no special experience, no ability to manufacture custom parts or print PCBs or something. You can build something like this in a day if you kind of have everything sitting there waiting for you. So let's walk through the pieces of this. There are 8 PVC tubes. Each one of those corresponds to a note on a musical scale. There are formulas for computing how long these should be. So you use those formulas to get kind of close, and then you tune the PVC pipes by just kind of cutting off slivers and hitting the end to make sure you have the right note. And one thing that's really neat that I like to point out to people about this is that you can see the musical scale visually here. So you can see these 2 areas on the PVC Marimba where there's a smaller gap between the notes. Those are the places on a musical scale where there's no accidentals, no sharps or flats. So that's specifically the gap between E and F and B and C. It's just kind of cool to see the wavelengths shown out like this. Under each of the tubes, there's a striker. These strikers need to move quickly in and out. They also need to be pretty affordable because I'm cheap. So I went with a thing called the linear actuator, which is just a motor that can go up and down. These are actually built for car door locks. So they're really affordable. I think I bought a package of like 8 of them for $15. Each set of 2 actuators is hooked up to a thing called an L298N. Hold on. If you think this is the point where things get really complicated or more boring if it's already boring you, I don't blame you for that, but let's quickly just look at how an L298N works so we can get into the code for it. Each of these devices is built to control actually 2 separate motors. So already the complexity of this L298N you can think of as split in half. The motor gets connected on one side, the power that drives the motor gets connected on another side, and then there are 2 inputs per motor that go over to the Raspberry Pi. And to describe the behavior of how you would control a motor, if the first input is true and the second is false, the motor turns clockwise, which extrudes the linear actuator. If you do the opposite, it goes and reverses back. If both are set to false, then the motor stops and doesn't consume, it only consumes a very small amount of voltage. And if both are true, I assume that it blows up. Just kidding. What will happen is it will make a very uncomfortable, unpleasant sound until you unplug it or it lights on fire. So the L298N, in analog mode at least, is very complex by appearance, but actually is really straightforward. Anyone that's been through like a college CS curriculum has seen something like this to describe Boolean algebra. This is really just describing the behavior of this motor. And you can really easily think about how this, again, is just a function. It's a thing that takes 2 inputs and produces one of 3 valid states for the motor and 1 blow-up state. Depending on when we change the inputs and how long we wait before switching them back, we can generate a strike on the bottom of one of the tubes. So let's check out the code. First, we create a mallet struct that holds references to the 2 pins that control one of the given actuators. And we create a convenience constructor for setting the pins as outputs and turning them to low voltage. By turning them to low voltage, we ensure that the pi and the voltage on each pin is in a known state before we get started. And we want to write some code to strike the PVC. So the way that we'll do it is first we want to pull the actuator down, causing a strike, which will take some time to actually move. Then we want to move the actuator back up, which will give the PVC a chance to resonate. Then we want to wait a similar amount of time for the actuator to move back to its its original state. Then we want to ensure the motor is turned off because we don't want to keep the motor keep running when it doesn't have to. So by varying the amount of times that are associated with each of these clock symbols, we can get different sounds out of the instrument. We can muffle a note, we can hit it more lightly by putting less time into the actual movement of it, or we can mute the resonance by hitting the note and then slamming the striker up against it. So the code here pretty much mirrors our description of this process. First, we set one motor to high, then we wait, then we set the other motor to high, then we wait, then we turn the motor power off. Similarly for the Marimba, it can be pretty useful to encapsulate this whole full device so that we can work with it. For this demonstration, we're wrapping the Marimba in a struct that contains a mapping between a musical note letter and the mallet object that corresponds with that note. And then to play a song, we would just go through each of the notes in sequence and strike the appropriate mallet when we get to the time, waiting for some period between each strike. Because strikes, and pretty much all hardware interaction for that matter, are asynchronous operations, we can make use of Go routines here when making a strike, which actually encapsulates the strike separate of the regular sequence of operations. So rather than the movement of the motor taking up time, we can lean on Go routines to make the strike happen at a particular time and then move on without worrying about how long the strike actually takes. This is really powerful for this example, and it's really powerful for a lot of other examples where you might program hardware with Go. So now we're ready to play a song. Does anyone know what this song is? I'm going to play it. Did you get it?
This Old Man. Right?
Yeah, it's This Old Man, that's right. Pretty good. No exaggeration, the code that I've showed you so far literally is the thing that's doing that. There is no more code. That is all of it. We can even play multiple tracks at once pretty easily. This is kind of a hacky answer, which I'll talk about in a second. But as things get more complicated and songs get longer, let me show you what this looks like for really quickly. So playing 2 notes at once, what we've done is we've taken the second track and put it in a Go routine so that the triggering of the second track happens and then the triggering of the first track happens and they run at the same time. So as long as the tracks have the same length, things should go okay. Cool. So anyone that's done a lot of work with asynchronous behavior probably sees the problem here, which is that as the song gets longer, the differences and gaps between the notes will increase and be different in weird, different ways. So over time, even though the song for a short song will stay together, for a longer song, it'll actually start falling apart as it goes on. As with any other asynchronous process, channels can be a pretty effective means of solving this problem. In the final version that I'll show of the Marimba code, we use channels to manage multiple parts of a song at once. We introduced this hand object over on the right side, which will get sent essentially each note as it needs to be played, which is then played over to the marimba, which finds the right mallet and strikes it. This keeps the chance of timing running away from the main Go routine low, and it removes the chance that parts of the song will deviate as it goes. So this is a little bit more complicated. That's it. Regardless of how far you want to go with the code, and you can go pretty far with it, I hope you see that the physical marimba is just another piece of engineering. Something that's made up of components that each individually are pretty simple to understand, but then when you put them together, become something that you can code and you can control, something you can have fun with, and something that you can share with other people. There are a variety of controls, sensors, lights, and buzzers. These are all really affordable. You can get them. They all pretty much function the same way. There's some inputs, and there's some outputs. You can make anything with just a little bit of imagination and the right combination of hardware. So just start simple and evolve your projects as you go. If you make something, I would love to see it. I hope you enjoyed this pretty quick introduction to hardware hacking in Go, and maybe it's inspired you to build something of your own. Thank you.